Very good morning, one and all. Today we are going to learn the chapter of what we can say electrical parameter networks, okay, as well as the passive networks. So we will simplify the few numerical on that circuit theory on that network analysis of the filters. So today we will simplify the few numerical on the filters. So we will see here which are that, how we can simplify the numerical on the basis of the low pass filter, high pass filter, band pass filter, and the stop band filters. Okay, so that we will see in this chapter. That is nothing but here the unit number 3, and the chapter name is electrical network parameters and the passive network. So we will try our best to continue the rest of the part which is related to the filters. And in the filter, two methods are used. One is known as the constant K, and other will be M derived method. So these are nothing but the M as well as the K derives are nothing but depending upon the characteristics impedance. These methods are assigned. Okay, so constant K means characteristics impedance will be constant for the throughout the network ideal case. Okay, so M derived is also the name by the scientists. So that method is there, and we can apply both the methods, that is a constant K as well as the M derived method for all the filters. Okay, in the T as well as the pi sections for the symmetry as well as the asymmetry network. Okay, so now we just take the first numerical number 1. Let's start. Note down. I will explain you, all of you note down there. Design a constant K. Design a constant K T section and pi section low pass filter. T section and the pi section low pass filter having cutoff frequency of 2 kilohertz, and nominal characteristics impedance of Z0, and nominal characteristics impedance Z0 is equals to 600 ohm. B part, find the frequency at which the filter offers attenuation. Find the frequency at which the filter offers the attenuation of a 19.1 dB. So this numerical is related to the filters and clearly mentioned that is a low pass filter is used. Okay, and here we need to apply the T and the pi section by using the which method, that is nothing but we need to design the constant K. Just now I have explained two methods. We are interested the two methods to apply on that all the types of the filters. Okay, so here the constant K is important, here the T and the pi section is important, and here which filter we are using, that is nothing but the low pass filters. And which parameters are given here, the cutoff frequency, that is nothing but 2 kilohertz. The characteristics impedance is the 600 ohm. So always be remembered twice, thrice. You must read the question and you must analyze yourself which parameters is given, what we need to calculate. So parameter given, cutoff frequency, and the characteristics impedance, and what we need to calculate, that is nothing but the designing part of the low pass filter in that T and the pi section. So if you're talking about the designing part, definitely few parameters will be there, the component will be placed, and in that component definitely LNC will be there. Okay, so that we need to calculate. So we can start likewise. The given that the FC is equals to 2 kilohertz and Z0 is equals to 600 ohm. For the low pass filter, next line, for the low pass filter, just note on this formula in the box, that is a cutoff frequency FC is equals to 1 by pi root of LC. 1 by pi root of LC. And the second formula which is related to the characteristics impedance is nothing but root of L by C. So here we are interested to calculate LNC for the low pass filter. So now, therefore, by observing these formulas, we can identify easily, we can find easily also. Okay, what we can find easily, that is nothing but LNC. So therefore, L is equals to Z0 divided by pi FC. Z0 is equals to pi into FC. And how we can calculate the capacitor? C is equals to 1 by pi FC Z0. 1 by pi FC Z0. 1 by pi fc z0. So here only the formula is mentioned, both fc and the z0, but directly they given the value of what you can say the fc as well as the z0. So either directly you can substitute, or you can get the lnc outside also. So here if you are taking outside, so what will be the case for the lnc, that is mentioned here. Okay, so here the z0 is a 600 divided by pi will be as it is, fc is nothing but the 2 kilo, so 2 into 10 raised to the power 3. Likewise, if you do with the calculation, you can cross verify yourself what is the answer and check this answer whether you are getting the same answer or not. So the 600 divided by 2 is nothing but 300 divided the pi is there, and this 10 raised to the power 3 will become as a 10 raised to the power upper, and denominator is there, go in the numerator, so it will be your the 10 raised to the power minus 3. Okay, so likewise this conversion will be there, and you will get as 95.5 millihenry. 95.5 millihenry. Similarly, for the capacitor is equals to 10 raised to the power 6. Okay, 10 raised to the power 6 divided by pi, this pi into 2 kilohertz, what we can 2 kilohertz and into the 600. Okay. So likewise, what you can do, because we want in the capacitor value will be always in the micro. Okay, so you need to take here, that is nothing but your the 1 by 1.2 pi into microfarad, that is nothing but 0.263. 0.263. 0.263. Have you got this answer? You may post. The B part you can simplify as attenuation in the dB can be converted, because here the attenuation is given frequency at which the filter offers the attenuation of 19.1 dB. Find the frequency at which. So here in this case we can find the frequency, but the attenuation is given in the dB. And if you want to convert into the nipper, then it is possible. So how it is possible? The attenuation in dB is equals to 8.686 into the attenuation in the nipper. This is the conversion. If you want in the nipper, so here will be dB into 1 by 8.68. If you want to take attenuation in nipper is equals to, so that will be 1 divided by 8.68. But here we are interested in the dB directly. So attenuation in dB is equals to 8.686 into attenuation in the nipper. So what is given the attenuation in the dB? That is nothing but 19.1. 19.1. So here will be 19.1 is equals to 8.686 into alpha. Alpha is nothing but the attenuation constant. So here, therefore, alpha is equals to 119.1 divided by 8.686. So you will get as 2.2 nipper. You will get as 2.2 nipper. Now, secondly, how we can find this, what we can say the normal frequency, because we need to find out the particular frequency at a attenuation, given attenuations. Okay, so what is the formula of attenuation constant? That is, attenuation constant for the low pass filter is equals to 2 into cos hyperbolic inverse of f divided by fc, where f is a normal frequency, whereas fc is the cutoff frequency. So now here alpha is given, just now we have calculated the alpha. Just now we have calculated the alpha. We know very well the fc. Now unknown parameter is nothing but the f. So in this way, the alpha is nothing but for the low pass filter 2.2. Nipper is given, already we have calculated, is equals to 2 into cos hyperbolic inverse of f divided by 2 kilo is there. Okay, so 2 kilo. At the end also you can take directly either the 2k, or directly you can write here the 2k, doesn't matter. Okay, fc is a 2 kilohertz. So likewise 2.2 into, so you just keep this cos hyperbolic at one side also, you can do it. So in this way you can calculate easily, that is the f frequency is equals to 2 into cos hyperbolic and the other parameter which you have calculated, that is nothing but 2.2 divided by the 2, that will be your 1.1. Okay, that will be your 1.1. So likewise you can get the frequency after substituting the value, after calculating the cos hyperbolic inverse and all, you will get 3.33 kilohertz. 3.33 kilohertz. Substitute the value of fc, substitute the value of alpha, that is a 2.2, and do the cross multiplication and the division and all other thing, and even what we can say the cos hyperbolic inverse and all. After doing all these things with the help of the calculus, you will be find f is equals to 3.33 kilohertz. Similarly, similarly, the end is nothing but what is given to identify, what we can say, to find out the designing part of your the low pass filter, and that too T and the pi section is given in the numerical. Okay, so that is possible. How it is possible? Just design the T and the pi section. We can design the T and the pi section. If you observe this section, you will be able to find this is the series arm, this one is also series arm, and this one is shunt arm. So two inductors are the series arm, whereas one capacitor is the shunt arm. Okay, so in the T section, already in the theoretical part we have studied for the series arm, this will be the L by 2, this will be the L by 2, and here will be the C. This case is for the low pass filter T and the pi section. We remember low pass filter, high pass filter, pass band filter, and stop band filter, all these things, the T and the pi section, series and the shunt arm will be different. So in the low pass filter, this is a T section. By looking this figure, you can easily identify these two are the series, one is the shunt. Okay, so L by 2, L by 2, and C. So already we have calculated the L. So whatever you got that value divided by 2, you just do it with divided by 2. So you will get one of the particular value, that is nothing but 47.77 millihenry. If you do in with the help of the CASI, you will be able to find the things. Okay, similarly for the next, that is nothing but your the what we can say, pi section. So in the pi section, this will be your the shunt arm, and these two are nothing but your the sorry, this one is the series arm, and these two are nothing but the shunt arm. So in the shunt arm, C by 2, here also C by 2, and here will be the L. Okay, so L will be directly you can write whatever you got, that whatever you got. Okay, and in the shunt arm, that is nothing but the capacitor. So whatever you got that value divided by 2, so you will get 0.131 microfarad both the sides, 0.131 microfarad, 0.131 microfarad. Okay, so these are the value in the T and the pi section for the low pass filter. Okay, so this was the numerical number 1, which was related to the low pass filter, and we have designed the T and the pi section by getting the value of your what we can say, the cutoff frequency, as well as your the characteristics impedance, and we have calculated the unknown parameter, the inductor and the capacitor value, because the inductor and the capacitor are the component which are in the T and the pi section for the designing part. Now go for the second unit. So let's start the numerical number 2. Note down, design a constant K, design the constant K T and the pi section for the high pass filter, T and the pi section for the high pass filter, T and the pi section for the high pass filter. FC is equals to 10 kilohertz. FC is equals to 10 kilohertz. FC is equals to 10 kilohertz, and characteristics impedance of a 600 ohm. Characteristics impedance 600 ohm, and phase constant of a 25 kilohertz, phase constant 25 kilohertz at a frequency of 25, phase constant of the filter at a particular frequency 25 kilohertz. And the last C part, in all the cases, what you need to find out, you need to find out the characteristics impedance at 25 kilohertz as well as the characteristics impedance at 5 kilohertz. Characteristics impedance at 5 kilohertz as well as the characteristics impedance for the 25 kilohertz, both the cases. Okay, so here how we can start here, they clearly they mention in the previous case low pass filter was there, here is the high pass filter, and the cutoff frequency and the Z0 we need to calculate. See the difference between these two, characteristics impedance is same, Z0 is equals to root of L by C, but the cutoff frequency is changed. In the previous one, the That's why 1 by pi of root of LC, but here 1 by 4 pi into root of LC is there. 1 by 4 pi root of LC is nothing but the cutoff frequency, and characteristics impedance is same here. Okay, if you observe the T and the pi section, you will be able to find the series arm is nothing but the capacitor, whereas the shunt arm is nothing but the inductor. In the pi section, the series arm is the capacitor, whereas the shunt arm is the inductor. So vice versa case is here, and here whatever you will get the value, you need to multiply with the 2, then only you will get this series arm. Similarly, whatever you will get the inductor value, you need to substitute here. Okay, but here also the opposite vice versa case, C will be as it is, and the inductor value you need to multiply with the 2, then only you will get the inductor value. So how we got this L and C, that we will see here by keeping the concentration on this given parameter, that is the FC, that FC, which is nothing but you are the 10 kilohertz, and the characteristics impedance is nothing but you are the 600, and we need to calculate the rest of the part depending upon 25 kilohertz as well as the 5 kilohertz. So here in this case, for the by looking the above equation, we can find for the high pass filter, we focus on the high pass filter. Okay, high pass filter, T and the pi section, and constant K. These three things are important. The method is a constant K, the sections are T and the pi, and the filter is nothing but the high pass filter. So in the high pass filter, the inductor can be calculated as L is equals to Z0 divided by 4 pi FC. So Z0 is already given, that is the 600, and 4 pi FC. FC is given. How much FC is given? So FC is given as 10K. Okay, so 10 into 10 raised to the power 3. So likewise, you can find easily, you will be find the inductor value 4.77 millihenry. If you do with the calci, you will be able to find 4.77 millihenry is the inductor value. Substitute the Z0, substitute the pi, substitute the FC. Similarly, if you want to calculate the capacitor value, C is equals to 1 by 4 pi FC Z0. Okay, so in this case, as this is in the micro, that's why we are taking here what we can say 10 raised to the power 6, otherwise no need. Okay, you can take directly here also. Later on it will be the 10 raised to the power minus 6. Okay, so 4 pi FC is nothing but again the 10 into 10 raised to the power 3 into Z0 is a 600, so 1 by so here will be the micro. Okay, so here you can take directly the micro term. Okay, because we need to represent the capacitor value in the micro, whereas the inductor value in the millihenry. So in this way, you can find that the capacitor is a 0.013 microfarad. Okay, so these are the two configuration of a T and the pi section. So you can substitute the component value, that is the inductor and the capacitor on the above circuitry. Okay, so now go for the B part, that is the second part. So in this case, that is characteristics impedance for the T section and the pi section, how we can calculate at a particular frequency. One time the particular frequency is given just to find out the characteristics impedance of a T and pi at a 25 kilohertz, whereas in the second case, the characteristics impedance at a T and the pi section with the help of the F is equals to 5 kilohertz. So first of all, we will go for the F is equals to 25 kilohertz. What is the formula for the what is the high pass filter characteristics impedance in the T and the pi section? So characteristics impedance Z0 at the T and the pi section can be calculated as a Z0 into, okay, Z0, or in many of the textbook they are referring the terminating impedance also. So Z0 into root of 1 minus FC by F. FC is again the cutoff frequency, F is the normal frequency. Okay, see the difference here. Here is the multiplication and here is the what we can say the division part. As we can observe easily in the T and the pi section, the series and the shunt combination, even the L and the C value, how they are different, how they are vice versa. So likewise, we can substitute all the values. Okay. So in this case, the characteristics impedance is a 600. FC is given, that is a 10K. Here is the 25K. So this KK will be cancelled out. 10 divided by 25 bracket square will be there, and that you can do with the help of calci, and then what is subtraction with the 1 and the root you can take, and then at the end you can multiply with the 600. So you will get, in short, the root term you are getting 0.84, and finally if you are going to multiply with the 600, you are getting as a what we can say 50, not 54, 540 something, it's a cut here. So here will be continuity, this will be the triple digits. Okay, ohm. Similarly, Z0 pi will be Z0 divided by root of 1 minus FC by F. So here 600 divided by, as this case already we have calculated 1 minus fc divided by f of square, that is a root of 0.84. So if you are going to substitute here the multiplication 600 into root of 0.84, whereas 600 divided by root of 0.84. So in this way you can get the T and the pi section of your the characteristics impedance, that is a 661 ohm. So now go for the same case, but the frequency will be different. Okay. So one more thing, apart from the characteristics impedance, we need to calculate the phase constant. So phase constant can be denoted by the beta representation. We know very well the propagation constant gamma is equals to alpha plus j of beta. Alpha is the attenuation constant that we have calculated. Phase constant is nothing but the beta. So beta will be equals to 2 sine inverse of fc by f. So again equals to 2 sine inverse of 10 divided by 25. So you will get one of the value that will be sine inverse, and you can multiply with the 2. So you will get as a 47.2. That is in the degree. If you want to convert same thing into the radian, that is available one of the button in the calculator. So you can do it. So you will get as in the radians 0.82. 0.82 in the radians. Okay. Similarly, the C part, which is clearly mentioned, what we need to calculate, we need to find out the attenuation constant at a particular frequency, that is nothing but the 5 kilohertz. So here the attenuation constant, we know very well the formula alpha is equals to cos 2 into cos hyperbolic inverse of fc by f, that we have seen in the previous slides. Attenuation constant denoted by alpha, phase constant denoted by beta. So attenuation constant is equals to 2 into cos hyperbolic inverse of fc by f. This we are repeating just because we want to find out the at a particular frequency, that is nothing but the f, that is of a 5 kilohertz. Change the frequency here. Okay, fc will be your what is given fc? 10k. Okay, fc is given as fc is given as a 10k, and f you need to take the 5k. So likewise 10k divided by 5k, then just do the division and do it the cos hyperbolic inverse, then multiply with the 2, you will find as a 2.6 nipper. 2.6 nipper. 2.6 nipper. Okay. So likewise, we have calculated in the first case, that is a designing component L and C. In the second case, we were interested the alpha and the beta, or Z0T and the Z0 pi. In the third case, we are interested in the alpha. Okay. So likewise, we have done the such of a different numerical. Now go for the numerical number 3. So what is given here? Here is also somewhat different numerical, that is for the band pass filter. Okay, BPF, band pass filter. So design at the constant K. Take the example. Design the constant K band pass filter. Design the constant K band pass filter. Design the constant K band pass filter having the cutoff frequency of having the cutoff frequency of having the cutoff frequency. I will tell you what is the cutoff frequency here. What they mention, it's not mentioned here. Somewhat cut is there, no? I will tell you soon. And the characteristics impedance of a 250 ohm. Characteristics impedance of a 250 ohm. Characteristics impedance of a 250 ohm. F1 is equals to 750. F1 is equals to 750. F1 is equals to 750. Z0 is equals to 250 ohm. Z0 is equals to 250 ohm. Z0 is equals to 250 ohm. That is already mentioned here, the characteristics impedance. So both the meaning is the same one. Okay. So what we need to calculate here? Design. What they are saying? Design a constant K. Okay. So what we need to calculate? We need to calculate the parameters of a designing part. Okay. So be remembered, if you are telling the designing to in designing the L and the C value, how they are connected in the series as well as the shunt. Okay. That is important so that we can calculate easily the inductor value, the capacitor value. Both we can find easily, the inductor value as well as the capacitor value. That is important here. So in the designing of the which filter we are using here, we are using the filter of your the band pass filter. So definitely my designing part will be different, definitely my figure will be different, definitely my the value of the inductor and the capacitor will be different. Okay, so similarly here, first of all, note down the heading, that is nothing but band pass filter comma constant k, band pass filter comma constant k, band pass filter comma constant k we are using. So how, what will be the design part that we will see here, whether we are see, this is the designing part. First of all, you just draw this figure, design of T and the pi section, design of T and the pi section of a BPF, band pass filter, design of T and the pi section, designing of T and the pi section for the BPF, for the BPF band pass filter. Now draw this figure first. So this is the series arm, here also series arm, here is the shunt arm. Similarly here, what we can say, the series arm is the inductor and the capacitor, same will be repeat here, the inductor and capacitor are in the shunt, are in the shunt. So what will be the case in the series arm? L1 by 2, L1 by 2 will be here. These two cases are same here, L1 by 2, L1 by 2. Getting 2C1, 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 2C1. Similarly here, L2, C2, L2, C2. What is L2? This value we will find later on, but only mention the value here. You just don't note down the value, okay? 11.37 something. You need to calculate first, and then you need to substitute there at the place of the value. Okay, so right at present, don't write anything. Only simply mention L1 by 2 for the series arm, 2C1 for the series arm, again the 2C1 as well as L1 by 2. Here L2 and the C2. Now vice versa case in the pi section. Okay, what will happen? This will be twice. This section will be twice, and middle will be L and C are in series. So series arm will be L and C. Series arm is the L and C. Shunt arm will be your the inductor and the capacitor. That will be 2L2 C2 by 2. 2L2 C2 by 2. Here also in the other section which is not visible, that will be the same for the pi. Same for the pi. That is a 2L L2 and C2 by 2. 2L2 C2 by 2. So what we need to do after the designing this part, we need to calculate the value of L1, L2, C1, C2. What we need to do? We need to calculate the 4 parameter for the band pass filter. That is nothing but L1, L2, C1, C2 in the series as well as the shunt. Now come towards the parameters which is given. So resonance frequency, that is nothing but the cutoff frequency. Resonance frequency or the cutoff frequency is equal to critical frequency, the root of F1 and F2. What is my, these are the two frequencies in which the band pass filter, that is nothing but the frequency will be passes. Okay, at a particular frequency from the F1 to F2, all the entire frequency will be passed. Previously and onwards, there will be the no frequency will be passes. Okay, so in short, you can see the F1 is given 750, and other which is not visible here, you just note on the other frequency is nothing but the 40 to 50, which is not visible at the side. So here the root of F1 F2, that is 750 into 4250, 750 into 4250. So you will get the answer 1785.3. Even you can do at 1.785 kilohertz. 1.785 kilohertz. 1.785 kilohertz. Similarly, for the other case, series arm total inductance. Series arm total inductance. Series arm where we have found, that is in the T section. That is in the T section. So series arm total inductance L1 is equals to Z0 divided by pi F2 minus F1. Z0 divided by pi F2 minus F1. F2 minus F1. So what is my Z0? That is a 250. Pi will be as it is. What is my F2? 4250 minus 750. So you will get as 22.7 something. That is the inductor na to millihenry. 22.70 millihenry. 22.70 millihenry. So we have calculated the series resonance frequency. that is a 1.785 kilohertz. We have calculated the series arm inductance denoted by L1, which we have seen the what you can say the slide, that is in the T section. Okay, L1. So Z0 divided by pi into F2 minus F1. Similarly, we need to calculate the shunt arm, which was the parallel. Okay, the shunt arm inductance can be calculated as, that is nothing but denoted by L2. Shunt arm total inductance denoted by L2 is equals to Z0 into F2 minus F1. Z0 into F2 minus F1 divided by 4 pi F1 F2 divided by 4 pi F1 F2. Now substitute the value of Z0 is a 250 into the difference between these two, that is nothing but the 4250 minus K 750. 4250 minus 750. You will get as 3500. You will get as 35. You will get as a 3500 divided by 4 pi F1 F2. 4 pi F1 F2. So 4 pi 750 into 4250. 750 into 4250. You will get 21.84 millihenry. 21.84 millihenry. 21.84 millihenry. Now these are the three parameters which we have calculated: resonance frequency, series arm total inductance L1, and series arm total inductance of shunt arm L2. Now go for the next. Series arm total capacitance, that is nothing but the C1. Series arm total capacitance is equals to C1 is equals to, now find out all the series arm capacitance value C1, all the shunt arm total capacitance value C2. So how we can calculate the C1? C1 is equals to F2 minus F1 divided by 4 pi Z0 F1 F2. See here the difference in the inductor, capacitor, series and the shunt. So F2 minus F1 divided by 4 pi Z0 F1 F2. So here will be the difference will be 3500 divided by 4 pi into 250 will be the Z0. F1 is the 750 and F2 is nothing but 4250. Likewise, you will get as 0.34 microfarad. 0.34 microfarad. 0.34 microfarad. 0.34 microfarad. Now second is nothing but the shunt arm total capacitance. Shunt arm total capacitance C2, that will be equals to 1 by pi Z0, 1 by pi Z0, F2 minus F1, 1 by pi Z0, F2 minus F1. So 1 by pi into 250 and difference will be your the 3500, you will get 0.363 microfarad, 0.363 microfarad. 0.363 microfarad. So likewise, we have calculated the inductance value, we have calculated the series and the shunt inductance value, we have calculated the series and the shunt capacitance value, we have calculated the resonance frequency and the other parameter, and also we have designed the what we can say the T and the pi section. Also we have designed the T and the pi section. Okay, so we need to remember in all the cases, all the three parts, what we have done. We have done the numerical on the low pass filter. We have done the numerical on the high pass filter. We have done the numerical on the band pass filter. In all the cases, the designing part is important. While we are talking about the designing, we should concentrate on the T and the pi section. We should concentrate on what should be my value of a L and the C. Okay, in terms of the notation, in terms of the formula. Okay. Now, secondly, what should be the formula of the low pass, high pass, band pass, and the stop band for the cutoff frequency? What should be the value of your the Z0 characteristics impedance in all the cases? And which method we are going to apply, whether we are using the constant K, whether we are using the M derived and all. So at present, today we have simplified only the method which we have used, that is nothing but the constant K. Why the name, the mention likewise the name itself indicating we are getting the characteristics and impedance of the constant value. Okay, and that constant value is nothing but the K, but we are representing in the form of the characteristics impedance. Okay, we can represent in the form of the characteristics impedance. So likewise, we have simplified Previously also many numericals, today also many numericals, still few numericals are left which is related on the M-derived filters. After completing the M-derived filters, we will go switch towards the attenuators. Okay, then later on the ladders and the other cascaded form, or the you can say the what we can say cascaded and network, or you can say the complex network and